Hi, today we're going to talk about arithmetic series. An arithmetic series is just the sum of an arithmetic sequence, meaning we're just adding all of the terms together. So we're trying to figure out what they add up to be, and that would be the sum of an arithmetic sequence or an arithmetic series. So there's a couple of kind of vocabulary words we want to make sure we recognize. First, that it is finite. Okay, finite means the series has an end. So it's going to have a last term. It's not going to go on forever and ever and ever. Versus an infinite series is going to continue without end, and it's never going to stop. So we'll be talking about a finite series today, meaning it has a fixed number of terms. Maybe we're going to add up the first 5 terms, the first 10 terms, the first 20 terms of a series. That's going to be a finite series. And then we're going to use the first term and the last term today. We need to know both of those, but that's the notation. A sub 1 means the first term, and A sub n means the last term. So to kind of introduce this concept, we're going to look at this particular sequence, which lists the numbers between 1 and 10. And when we're finding the sum, notice the notation changes. S sub 10 means the sum of the first 10 terms in that sequence. So I've listed them out: 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, 8, 9, and 10. We're adding all of those together. Now go ahead and pause the video for a second. I want you to think about what is the fastest way you could possibly add those together. So if I was going to try and add these together, I think it's best to do this in pairs, meaning 1 and 10, 2 and 9, 3 and 8, 4 and 7, and 5 and 6. And if you look at each one of those pairs, if we write that down, we can say this is 1 plus 10, 2 plus 9, 3 plus 8, 4 plus 7, and 5 plus 6. And each one of those pairs adds up to be 11, so there are 11 plus 11 plus 11, and there are 5 of them. And so we can say this is 5 times 11, or 55. And what I want to make sure you see in particular is that this number right here, the 5, is the number of pairs, and the 11 is the sum of the first and last term. Meaning, if we were going to extend this series, instead of going the first 10 terms and we did the sum of the first 100 terms, think about how many pairs it would be. If there's 100 terms, there would be 50 pairs. And then the first term plus the last term, if we wanted to figure out the sum of the first 100 terms, we'd simply say 50 times 101, or 5,050. And so this applies to any arithmetic series as long as there's a common difference between the terms, and obviously our common difference here is 1. We're adding 1 to get the next term. So in general, here's your formula. We're going to say n over 2 times the first term plus the last term. And just to be clear here, this part here is the number of pairs. The n over 2, if there's 100 terms, there's 50 pairs. We're just dividing it by 2. And then it's the first term plus the last term, just like we did above. So n is the number of terms. A sub 1 is our first term. And A sub n is the last term. And the one thing you want to remember is an infinite arithmetic sum does not exist, or you can say it diverges. So if it's infinite, we cannot find its sum, but if it is finite and stops, meaning we take the sum of the first 10 terms, or first 20 terms, or first 100 terms, we can definitely calculate that. All right, let's take a look and see if we can apply that formula to find the sum in example 1. So it looks like we have 15 plus 21 plus 27, and it goes on all the way up until 63. So if you think about the formula above, there's three things we need to know. We need to know the first term, which is 15. We need to know the last term, which is clearly 63. And we also need to know the number of terms. But we don't know how many there are in that series. So what we can do is we can recognize that there is a arithmetic series, and it looks like we are adding 6 each time. So I'm going to use the nth term expression that we used earlier in this chapter. I'm going to say the nth term of an arithmetic series or arithmetic sequence would be a sub n plus a sub 1 plus n minus 1 times d. And I'm going to fill in what we know. We want to figure out what number that last term is. So we want to figure out what number 63 is. Our first term is 15. And we want to figure out our n value for that last term. Common difference is 6, and we're going to see if we can simplify this. If I subtract 15 and divide by 6, I wind up getting 8 is equal to n minus 1. And then if I add 1, I get 9 is equal to n. So what that tells me is that there are 9 terms in this series, and I can find the sum of the first 9 terms. So using that, I'm going to say 9 over 2, just using the formula from above, times 15 plus 63. And if we simplify that, that winds up being 351. All right, let's take a look at the one below it. It says find the sum of the first 20 terms in the sequence, 8, 5, 2. And it looks like this is arithmetic, and it looks like to get the next term, we subtract 3. So our common difference there is negative 3. That's what that's telling us. And let's see if we know the kind of the 3 components of the formula. First off, it said we want to find the sum of the first 20 terms. So we know n is 20. We know the first term is 8, and the nth term or the 20th term, we don't really know. So we need to figure out what that last term is going to be in this series. So again, we're going to go back to that same formula where we have the first term plus n minus 1 times d, and we'll fill in what we know. We want to find the 20th term. First term is 8, and we have 20 minus 1, or if you want to write 19, you can write 19 in there. And we multiply it all out. So we want to find the 20th term here. Negative 57 plus 8 would be negative 49. So that is going to be our nth term. And now we can complete the formula. The sum of the first 20 terms would be equal to 20 divided by 2, or n divided by 2, times the first term, which is 8, plus the last term, which we know is negative 49. And this winds up being 10 times negative 41, or negative 410. All right, this next example requires kind of a little bit of an introduction to summation notation. So the big letter on the left there is called a Greek letter sigma. It's an uppercase sigma, and it means summation. So this is the notation we use for summation in mathematics. And it looks really, really fancy and complicated, but is not as complicated as you would make it. This n squared, you're used to seeing this as kind of the rule for the nth term. And we've done that before and said a sub n is equal to n squared. If we were going to generate terms from this, we would say the first term, when n is 1, 1 squared would be 1. Second term, 2 squared would be 4. 3 squared would be 9. 4 squared would be 16, and so on. We've done that from the beginning of this chapter. So that's just the rule for our terms. And then it tells us specifically where to start. This number on the bottom right here is our starting point. We're going to start with n is equal to 3. So if we plug in 3 first, we're going to get 3 squared And then the next term would be 4 squared. And we're going to go all the way until we get to our ending point, which is the upper limit of 5. So we start at 3, stop at 5, and we're just plugging those values into the n squared expression. And so obviously 3 squared would be 9, 16, and 25 for 4 squared and 5 squared respectively. If you add those all together, you'd get a total of 50. So just make sure you follow the rule that is there inside the summation notation. So we're going to do that here with this next problem. We're going to start at 1. I'm going to plug 1 into the expression. And if I did that, 7 minus 2 times 1, or 7 minus 2, would be 5. Plug in 2 next. 7 minus 2 times 2, or 7 minus 4, would be 3. And if you kept going, you would see that this pattern continues. And if you plugged the last term in, which is when n is equal to, or in this case j, is equal to 16, 7 minus 32 is negative 25. So we know how many terms there are, and we know that there are 16 terms, because it goes from 1 to 16. There's 16 there. Our first term is 5. And our last term, which would be a sub n, or a sub 16, we know that's negative 25. We have everything we need to know to be able to calculate the sum of this expression here. So let's see if we can do that. The sum of the first 16 terms would be equal to our number of terms, which is 16 divided by 2, times our first term plus our last term. And we wind up with 8 times negative 20, or negative 160, which would be the sum of the first 16 terms in this series. All right, they're asking us for the summation notation on this last example. So before we can write the summation notation over here on the right, we're going to see if we can answer these questions. This is kind of the thought process for going through a problem like this. First term looks like it is negative 5. Common difference here, it looks like to go from the first term to the second term, we added 7. Let's just double check that that's consistent. Looks like we added 7 on the second and on the third as well. So our common difference, D, is 7. So using that, we're going to write the explicit formula, which is our first term plus n minus 1 times D, which is 7. And if you simplify that, multiply it all out and simplify, you end up getting, looks like 7n minus 12. So using that, we should be able to write the rule at least. And then the last term, that was given up here, that's 268. So we should be able to figure out how many terms are there. So we know that the nth term expression is 7n minus 12. And we need to figure out what term number 268 is. And that's going to tell us how many terms are in this whole series. So I'm going to add 12. I get 280 is equal to 7n. And if we divide 280 by 7, we get 40. So that tells us this is a sum of 40 terms. Let's see if we can write this. We're going to start with k equals 1 and go all the way until k equals 40 because we want 40 terms in this series. And the expression that we got for the nth term, it's going to go right here. That is 7n minus 12. And that's the summation notation for this series. And again, if you want to check it, plug in k is equal to 1 here, or let's make this a k instead of an n. If we plug in k is equal to 1, we get 7 minus 12, or negative 5. That checks out with the first term in our series. If you plugged in 2, you get 14 minus 12, or 2. If you plugged in 3, you would get 9, and so on. You can check the 40th term. If you plug in 40, you should get the last one, which is 268.